By the Bronsted-Lowry definition, we say that an acid is anything that when we dissolve it in water, it produces H3O plus or hydronium ions. So, for example, if I have some acid, HA, and I put it in water, then it will have an acid-base reaction with the water to make H3O plus. So this hydrogen here is added to the water, and we will make our A minus. The acid here, the HA, is the conjugate acid, and the A minus here we call the conjugate base. I've drawn equilibrium arrows here, and this particular equilibrium for an acid-base reaction we call the Ka, or the acid dissociation constant. In this case, Ka is equal to the concentration of H3O plus times the concentration of A minus over the concentration of HA. So this is just the products divided by the reactants. I haven't included water because water has a roughly equal concentration and it won't have an effect on our Ka. So this is our Ka. Now, if I had a base by the Bronsted-Lowry theory, a base is something that when you dissolve it in water will make OH minus or hydroxide ions. So for example, if I have some base A minus, and I put it into water, then I will have an equilibrium reaction that will give me OH minus. So here the water has lost one of its hydrogens, and that hydrogen is going to be attached to the A. So now we have HA on this side. So this is a base, and here we have an equilibrium constant, and because it's a base, we call it a Kb. So this is the base dissociation constant, and that again is equal to the product, so OH minus times the concentration of HA over the reactants, but ignoring water. So the reactant is A minus, and that is Kb. Now, because water is so common and it can act as both an acid and a base, we give it a special name for its acid dissociation constant. So we can imagine that if we take water and we put it in water, some of it will self-ionize to give H3O plus and OH minus. Now the equilibrium constant here we call Kw, so the equilibrium constant for water, the W is for water. So that is equal to the concentration of the product, so H3O plus and OH minus, and then divided by the concentration of the reactants. But both reactants are water, so we don't include them. So here at room temperature, this equilibrium constant has a value of 10 to the power of negative 14. You'll see that if we take Ka and multiply it by Kb, this is equal to, so I'm going to get the first bit from here, so H3O plus times A minus over HA, and then I'm going to multiply by Kb, which is OH minus, times the concentration of HA over the concentration of A minus. Now, if we cancel out, we have HA and HA cancel, A minus and A minus cancel. So what we get is that this is equal to the concentration of hydronium times the concentration of hydroxide. Well, we see then that this is just equal to Kw, which is 10 to the minus 14. So anytime you have a conjugate acid and a conjugate base, so that means an acid and a base that differ from each other only by one proton, so by one H. So for example, this A minus and this HA, so they differ only by one having a hydrogen and one not having a hydrogen. If you take the Kb for the base and multiply it by the Ka for the conjugate acid, you'll always get Kw, which is 10 to the minus 14.